Welcome to this explainer. Today we're diving into a very real problem. You look at a perfectly elegant mathematical model for heat transfer, right? And then you try to apply it to an actual, messy, turbulent pipe in the real world, and theory completely clashes with reality. Well, today we're going to bridge that gap.
So here's the big question. What do we actually do when complex fluid dynamics literally break our analytical math models? In a perfect world, sure, we'd solve every convection problem with a neat little differential equation. But we don't live in a perfect world. The reality of engineering is full of turbulence, bizarre boundary layers, and property variations that make pure math impossible, or just, way too tedious. So we pivot. We rely on experimental data to build empirical formulas.
To keep things moving, here's our roadmap for this explainer. First, when analytical math fails. Second, the mixing cup concept. Third, opening up the pipe flow toolbox. Fourth, navigating entrance effects. And finally, flow across cylinders. Let's get into it.
All right, part one, when analytical math fails.
Let's just validate a very frustrating reality right off the bat. Getting perfect analytical solutions to convection problems? Yeah, often impossible. When the math fails us, we have to rely on shrewd inferences drawn from dimensional analysis. But, as you can see from the source material here, physical intuition is absolutely your ultimate guide. You can't just throw a bunch of numbers at a wall and hope they stick. You really have to intuitively grasp what the fluid is doing. Like, how's that boundary layer behaving? How's the pressure shifting? Long before you can even think about organizing your experimental data into a useful formula.
Now, what's genuinely fascinating here is how we use dimensional analysis as basically an engineering hack to turn raw data into usable formulas. We're essentially reverse engineering the math. We start by guessing a functional form based on similar problems we actually do understand. Then we run the experiments, tweaking the pipe diameter, the fluid, the mass flow rate. And finally, we use log-log plotting to extract the missing constants and exponents for crucial parameters, like our Reynolds and Prandtl numbers.
And this right here, this is the scientific method in action. Taking a look at this log-log plot of the Nusselt, Reynolds, and Prandtl numbers, you can see how it derives our final empirical correlation. Since we assumed a power function relation, plotting this raw data on logarithmic scales gives us these beautiful, predictable straight lines. The slope gives us our exponents, and the intercept gives us our constant. It's just a brilliantly simple way to wrangle chaotic, turbulent data into a clean, easy-to-use line.
Moving right along to Section 2, the mixing cup concept.
To really get a handle on internal closed-channel systems, we've got to define a pretty crucial concept. See, because temperature varies all along a tube's length, we absolutely must rely on the bulk temperature, or the mixing cup average, to calculate our heat transfer. Think about it. Fluid flowing right up against the hot wall of a pipe is going to be significantly hotter than the fluid coasting right down the center. If you were to literally chop off a section of that pipe, catch all the fluid in a cup, and stir it up until the temperature equalized, well, that average temperature is your bulk temperature. It is the absolute anchor for all of our internal pipe flow calculations.
So the total energy added over a specific length is directly tied to this bulk temperature difference and the mass flow rate. You can easily see the fluid entering at bulk temperature 1 and leaving at bulk temperature 2. If we know the mass flow rate and the fluid-specific heat, evaluating the heat transfer simply becomes a matter of tracking how much that mixing cup temperature goes up or down from point A to point B. Pretty straightforward, right?
Okay, Section 3, the pipe flow toolbox. Armed with that foundational mixing cup concept, we can now crack open our pipe flow toolbox. I want you to treat these equations, like Dittus-Boelter for smooth tubes or Patukoff for rough ones, not as rote memorization, but as highly specific tools for highly specific jobs. I mean, you wouldn't use a hammer to drive a screw, right? Same logic applies here. You definitely wouldn't use the simple Dittus-Boelter equation if your pipe has significant internal roughness, or if your flow is still totally laminar. You've got to diagnose your flow regime first by calculating your Reynolds number, and then pull the correct empirical equation from this toolbox.
Looking at this friction factor chart, it becomes super clear why empirical equations have to adapt to different roughness conditions and transition zones. Honestly, this chart is kind of a map of chaos. Over in the laminar zone on the left, everything is nice and predictable. But as that Reynolds number cranks up, the curves fan out wildly depending on the relative roughness of the pipe. Our heat transfer equations have to account for this friction. Why? Because friction means turbulence, and turbulence dramatically increases the mixing, which means a massive spike in the heat transfer rate.
But wait, friction isn't our only headache here.
We have to remember that extreme temperature differences actually change the fluid's viscosity between the wall and the center. Imagine you're heating a liquid. The liquid right next to that hot wall gets less viscous and actually flows faster than the cooler, thicker liquid in the center. This totally distorts the standard velocity profile. Because of this, we're forced to use specialized corrections, like the Cedar-Tate relation, which explicitly compares the fluid's viscosity at the bulk temperature to its viscosity right at the wall. It's a literal game changer for accuracy.
All right, on to Section 4, Navigating Entrance Effects.
So, we also need to address the wild complications that pop up when flow just hasn't had enough length to fully develop. Comparing these two charts visually reveals a massive takeaway. Thermal entrance lengths are significantly shorter for turbulent flows than for their laminar counterparts. When fluid first enters a heated pipe, the thermal boundary layer hasn't really formed yet, which means heat transfer is incredibly high right at the entrance. As the flow moves down the pipe, that boundary layer grows and the heat transfer rate finally stabilizes. In turbulent flow, that's on the right, the intense mixing forces the flow to develop and stabilize super quickly. But in slow, smooth, laminar flow on the left, it takes much longer for the heat transfer to finally settle into a constant rate.
Because these short tubes haven't reached a constant Nusselt number yet, engineers have to rely on very specific charts to accurately model the heat transfer. For laminar flow, we rely on the inverse Grates number, which actually factors in the physical distance down the tube. For turbulent entry, it leans heavily on the Prandtl number. Basically, the higher the Prandtl number, the shorter the entry length, meaning the flow develops its thermal profile much faster.
Finally, let's hit Section 5, Flow across cylinders.
Let's step completely outside the pipe for a minute. Unlike internal pipes where the fluid is safely contained, cylinders in crossflow force us to account for intense boundary layer pressure gradients that drastically alter the velocity profile. Picture this. When fluid hits the front of a cylinder, the pressure drops as the fluid accelerates around the curve. But as it hits the back half, the fluid suddenly has to push against an increasing pressure gradient. Eventually, the fluid just loses its momentum. The transverse velocity, the velocity parallel to the surface, drops completely to zero, and the flow actually reverses direction. It's wild. And this graphic pinpoints the exact physical moment of flow separation, where the momentum of the fluid simply cannot overcome that increasing pressure. Notice the velocity profile arrows here. As the fluid travels along the curve, the velocity gradient right at the wall gets smaller and smaller until it literally hits zero. That 0 point, that is the separation point. The fluid literally rips away from the surface of the cylinder.
Past that separation point, the flow becomes completely chaotic and turbulent, and this completely transforms the heat transfer characteristics on the back half of the cylinder. Notice how the flow rolls back onto itself in the wake, creating these swirling vortices? This means you've got smooth, predictable heat transfer on the front of the cylinder and chaotic, turbulent heat transfer on the back. It perfectly encapsulates exactly why we need robust empirical data. Pure math alone would seriously struggle to cleanly model that swirling vortex wake.
So, as we wrap up this explainer, I want you to ask yourself a question. How do the experimental data and dimensional analysis we just explored directly shape the design of the everyday heat exchangers keeping our modern world running? Every single time your car's radiator efficiently sheds heat, or a massive power plant safely manages its thermal loads, it is relying on these exact empirical relations. The math might be incredibly messy and the experiments are definitely complex, but the physical insight derived from these concepts is literally what makes modern engineering possible. Thanks for joining me, and keep looking for the physics behind the formulas.